We're going to take a look at bacteria and viruses next. Now, these notes are going to be divided in half. We're going to start with viruses because that's a much more timely topic, and then we'll talk about bacteria. Before we start, I want to make sure it's clear. We tend to group viruses and bacteria together because they both cause diseases, but they're actually very, very different objects. Hopefully you remember, viruses are non-living, but bacteria are living. So that tells you they're two very, very different things, but because they both cause diseases, we will lump them together. So first thing, viruses are made up of only a protein coat surrounded by either DNA or RNA. Now it's kind of interesting. Some viruses only have RNA, they don't have DNA, and there's a wider variety of genome types in viruses than there are in any other type of living thing. Well, they're not even living. So the reason viruses aren't considered living is because they're missing a lot of the characteristics of life. They're smaller than cells, so they don't have organelles. They don't maintain homeostasis. They don't perform metabolism. Any energy they need, they take from the cell that they've invaded. They can't even reproduce on their own. The cell has to make them. So getting back to what I was saying about the makeup of viruses. So they're only a protein coat surrounded by either DNA or RNA. Some of them are also surrounded by a cell membrane. So as they escape from the cell that makes them, they steal some of that cell's membrane, so they might also be surrounded by that. Now, the thing I want you to focus on right now is this virus right here. You're going to see a lot of diagrams with that virus. Now, I want you to see, it's probably hard to see because it's so tiny, but that's labeled bacteriophage. So hopefully from that name, you can tell that bacteriophages are viruses that infect bacteria. Now, most of the pictures we're going to see are actually going to be of viruses that are like that. But why bother looking at bacteriophages when they don't infect our cells? They infect bacteria. Well, surprisingly, a lot of research has been done on bacteriophages. We've learned a lot about viruses from those. And so despite the fact that they don't infect humans, there's actually a ton of research about bacteriophages, and so that's what you'll tend to see diagrams of instead of other viruses. Now let's take a look at viral replication. So viruses cannot reproduce on their own. They use a cell to create more viruses. So they infect a cell and turn the cell into a virus-making factory. So let's take a look at the steps of virus replication. So step one is attachment. So the virus attaches to the cell membrane. Step two is entry. So there's two different ways that a virus can enter a cell. Either the virus latches onto the cell membrane and tricks the cell into taking it in by the method of endocytosis, where it surrounds the virus in a membrane and brings it in, or it just injects its DNA directly into the cell. So you can see here that bacteriophage injecting its DNA, and the protein coat of the virus doesn't enter the cell. So either way, the DNA of the virus is in the cell, whether it's the whole virus or just the DNA. Second is replication. So the cell is now reprogrammed to copy the viral DNA. So DNA replication, you know that process. And then that viral DNA is used to make viral proteins, so protein synthesis. And so this is how the virus is getting the cell to make more viruses. So step four is assembly. Once we have the viral proteins, the viral DNA or RNA, then we're going to put them all together to make the viruses. And then the last step is release. The viruses either escape through the membrane, surrounded by some of the cell membrane. So almost kind of a cross between endo and exocytosis. It's exiting the cell that way. Or they burst out of the cell, killing it. So this is one of the ways that viruses are damaging your body, is by killing the cells after they or as they escape from the cell. So now there's two different reproductive strategies that viruses can follow, either the lytic cycle or the lysogenic cycle. So let's take a look at what these two are. So with the lytic cycle, the virus infects the bacteria or the cell, any cell. The DNA is injected into the cell. The cell makes those viruses, and then those viruses escape, and they just continue this cycle. Well, the lysogenic cycle is a little bit different. So the virus injects its DNA, but that DNA becomes part of the cell's DNA. So notice it's just hiding in that DNA. And so then it doesn't do anything, doesn't make viruses, but when the cell reproduces, that DNA is reproduced with the cell. So now both cells have that virus's DNA. And it just continues on that way with the DNA in that cell. So the lysogenic virus can continue this way without any symptoms, any sign of the virus, and the virus is just hiding in your DNA as your cells continue to reproduce. Well, what can happen, and this is not fully understood why this happens, just for some unknown reason, the DNA will pop out of the cell's DNA, and then the cell starts to reproduce viruses. So a lysogenic virus can then go into the lytic cycle. Now, a lytic virus can never go into the lysogenic cycle, but lysogenic viruses randomly move to the lytic cycle. Now, the scary thing about this is if you take a look at this, is there any virus present? No. And so can you get rid of the virus? No, because there's no virus to get rid of. And so you can never fully get rid of a lysogenic virus. Once you get that virus, you have it for life. So those are viruses like HIV, herpes, things like that. One type of herpes, it's different from the type you tend to think of as cold sores. Cold sores you might have at some point, and then they go away, and you don't have them for a while, and then all of a sudden, for no known reason, cold sores pop up again. It is a lysogenic virus. And so lytic viruses you can get rid of because there's always going to be viruses in your system, but lysogenic can permanently hide. Now we've already talked through the next couple of slides, so I'm going to encourage you to pause so that you can write these, move on at your own pace. So vaccines, let's get into this because this is pretty exciting stuff because this is such a hot topic right now. Because viruses aren't living, they cannot be killed by antibiotics. So think about it, right there in the name, bio, life. Antibiotics can only destroy living things. So bacteria, and there are a few antibiotics against fungal infections. But antibiotics cannot do anything for viruses. And there are even very few medicines against viruses. So like there's Tamiflu against the flu, but even that, you have to take that within 1 or 2 days of getting the symptoms or it's not going to do anything for you. There are some medications against COVID, but again, not very many medicines to help with viruses. So for the most part, your immune system has to fight the virus itself. So let's start by taking a look at the classic form of vaccine. So the Johnson & Johnson COVID vaccine is the classic form, so attenuated. So most vaccines are attenuated. That means a weakened form of the virus. Highlight that definition right there. So attenuated vaccines, they essentially they damage the virus to the point where they're just giving you these surface proteins. So that's these little spike things coming off of that virus. So the surface proteins act like the ID tags on the virus. It's kind of like when we talked about blood cells, and we talked about the A protein, the B protein, the RH protein on the surface of your cells. Similar concept. So the purpose of introducing those proteins into your body is through trial and error. Your immune system is going to figure out which antibodies match the proteins on the surface of the virus. Remember, antibodies and those proteins, they're both proteins. And so they have to have a lock and key fit. If it's not the exact right shape, it's not going to match. And so giving a damaged virus to your cells gives your immune system time to try out and go through trial and error to find the right antibody without that virus causing damage to your cells at the same time. So then once the antibody recognizes and binds to the virus or just those proteins, it alerts the white blood cells to destroy the virus. So it acts like a beacon and says, here it is, white blood cells, come destroy this. So now once the immune system finds the correct antibody that matches that protein, then your immune system is going to make memory B and T cells to remember how to make that antibody the next time you're exposed to that virus. And so once it knows exactly which antibody, it doesn't have to go through that trial and error process, and so it can make the antibody very quickly, and it can destroy the virus the next time before it has a chance to cause any damage, before you even realize that you're sick. That is the power of a vaccine, because those antibodies that were made, those will only last in your body for 3 to 6 months. They're proteins. They'll get broken down and recycled. And so the antibodies aren't the power. The memory B and T cells that remember how to make those antibodies quickly, that's the power of the vaccine. So now let's take a look at the new style of vaccines, the mRNA vaccines. So the new Pfizer and Moderna vaccines, those are mRNA vaccines. Now there's a lot of hoopla about these. People are very upset about them because mRNA vaccines are new. Well, they're not really new. They've been being researched for 20 years. So it's not something that they just rushed out into the public, but it's the fact that they've never been used on the public previously that they seem so new and foreign to people. So like we did with the lytic and lysogenic cycle, we're going to talk through the diagram and then I'll give you guys the writing and you can pause and write it down. So let's take a look at this picture. So here we've got the virus, and this is the spike protein right here coming off of the virus. So they're going to take that protein and reverse engineer it. They're going to figure out what is the mRNA that encodes for how to make that protein. Now you remember we learned about mRNA. We learned about how that codes for proteins. So that's what we're taking a look at right now. So they take that mRNA, they put it in kind of like a cell membrane to protect it as it's inserted into your body. And then that cell is going to take in the mRNA. And then with that mRNA, it's going to go to the ribosome. The ribosome is going to make the protein coded for by that mRNA, and then that protein is going to be placed on the surface of the cell. So now antibodies can come and attempt to recognize this protein. And then once they find the correct antibody, then memory B and T cells can be made for how to make the antibody against the coronavirus. Go ahead and pause so that you can copy down the steps. So that mRNA does not last in your cell for very long. Any mRNA in your cell will be broken down by the cell after just a few days. Otherwise, it's going to sit around and your cell will keep making proteins after proteins after proteins far more than you need. That's wasteful. And so the mRNA for the coronavirus will not last in your cells very long. Now, a lot of people are very worried about this mRNA. They think that it will change your DNA. So let's address that fear. I want you to think about, where is mRNA made? Hopefully you remember transcription occurs in the nucleus. The DNA is copied into mRNA. Well, we already have the mRNA. mRNA never goes back into the nucleus. And so this mRNA will not enter your nucleus. So if it doesn't enter your nucleus, it can't alter your DNA. So that mRNA can't alter your DNA. It can't stick around for very long. And even after a few weeks, that spike protein will also be broken down. So the only thing that will last after that is the antibodies, and those will only last for a few months. The memory B and T cells are what last longer. This is the key thing I want you to take away about vaccines. Vaccines can only prevent a virus by teaching your immune system to fight it. Underline that, highlight that, put a star next to it. It cannot fight a virus once you have it. So I want you to think about it this way. Let's say you have COVID and you take the COVID vaccine. Well, your body is already trying to learn how to fight COVID with the real vaccine. So adding with the real virus. So adding the vaccine is only adding more material for your cells to have to learn how to fight. So that's not helping it. It's just taxing it more. So vaccines cannot treat a virus. They can only teach your cells how to fight it ahead of time, so that when you actually have that virus, then your immune system can fight it faster. In fact, if you have COVID and you take the flu shot, that's actually making things worse, because your immune system is trying to learn how to fight COVID, and then you give it the flu shot and now it has to try to learn to fight the flu. It doesn't know that that vaccine is fake. So it's trying to fight it as if you have two viruses and you're overtaxing your system. So that's why you should never take a vaccine when you're sick. There's also very few vaccines for bacterial diseases. So for the most part, there's not really only a few vaccines against bacterial diseases.